Today's lesson is 6.6, Graphing Rational Functions, Part 2. Some graphs of rational functions are not hyperbolas. The focus of this lesson is going to be on my vertical and horizontal asymptotes, my x and y intercepts, and any holes that the function can have. Before we go ahead and take a look at our 3 examples today, we have to learn how to find our horizontal asymptotes when we do not have h and k to help us out. We're going to compare the degree of the leading terms of my numerator, which is p of x, and my denominator, which is q of x. There are 3 different possibilities, which gives us 3 different possible horizontal asymptotes. So if my numerator is greater than my denominator, then there is no horizontal asymptote. If my numerator is less than my denominator, then the horizontal asymptote is the line y equals 0. And if my leading terms are the same degree, then the horizontal asymptote is the line y equals the leading coefficient of p dividing by the leading coefficient of q. How do I find my vertical asymptote? Well, I need to determine the value or values for which my function is undefined. To do so, I'm going to factor the denominator if needed, and then I'm going to set each factor equal to 0 and solve. Those would give me my vertical asymptotes. Let's go ahead and get started. In our first example, we are asked to graph g of x equals 2x minus 1 over x plus 4. We're going to go ahead and find the asymptotes, and then once we have the graph, we're going to go ahead and talk about our domain and range. I like to always start by writing down what is p of x and what is q of x. Once I have them written down, I want to make sure that they are in standard form. That means that the variable, my x's, has its highest degree first, and then it goes in descending order. So let's say you have x to the 5th. It would have to be first, and then you would put x to the 5th, 4th, 3rd, 2nd, 1, just x, and then no x, which would just be your constant. So it'd have to go 5, 4, 3, 2, 1, none with your exponent. Now notice that neither one of these x's has an exponent because it is invisible, it's 1. And so after 1 becomes 0, which would mean my constants. These are both in standard form, which makes this my leading term and that my leading term. The degree is the exponent. Both of them have the exponent of 1. So both of their degrees are simply 1, which means when I go back to look at that last page, I'm going to go ahead and compare my numerator to my denominator. The degrees are equal. So that's going to tell me what my leading coefficient is, what my horizontal asymptote is. I need to find my leading coefficients next. My leading coefficient is simply the number in front of my leading term. Okay, so for this one, it would be 2. Oops, there we go. And for the other one, my leading coefficient would be the invisible 1 that is there. All right, so going back to find my horizontal asymptote, it's the line y equals my leading coefficient of p divided by my leading coefficient of q, which would be 2 divided by 1. 2 divided by 1 is simply 2. There's my horizontal asymptote. To find my vertical asymptote, I am going to go ahead and take my denominator, which is q of x, and I'm going to factor it if I need to and set my factors equal to 0. Well, this already is a factor, so all I have to do is set it equal to 0 and solve, because this would make it undefined. Well, there we go. There is my vertical asymptote. Okay, let's go ahead and graph those, and then I'll show you some ordered pairs that I've already found. because I think you guys have got a good grasp on how to do Desmos. There's my line, x equals -4 and y equals 2. There we go. Okay, so some ordered pairs that are on this graph are -1, -1, and -3, -7. There we go. And so it looks something like this. And then -7, 5, -7, 5, and -5, 11, which is probably about up here somewhere. So then it did something like that. All right, remember my domain are my x values. These are my x values. So if I'm looking at my graph, it's everything except this guy right here. Everything except this guy right here. So negative infinity to -4, union -4 to positive infinity. Okay? This part gets this stuff. This part gets all that stuff. All right, my range are my y values, and it's going to be everything but my +2 of my asymptote. So it's going to be negative infinity to 2, union 2 to negative infinity. Let's take a look at another example. Let's go ahead now and graph the function g of x equals 3x squared plus 10 over x squared minus 1. We're once again going to find our asymptotes, our intercepts, our domain and range. We're going to start the same way by writing down both p of x and q of x. The nice thing about Alex is it's going to be already in standard form for you, so you're not going to have to really worry. It's always a good idea to go ahead and look at P of X and Q of X and ask yourself, can I factor? So to factor P of X, the 3 and the 10 would have to have a common factor. 1 times 3, 1 times 10, 2 times 5. Their only common factor is the 1, and if I divide by 1, it's not going to change. So that one is not factorable. This one, however, q of x, this is the difference of squares. This is x times x, which is a perfect square, and this is 1 times 1. And what's happening is notice that it's missing that b term, right? It's ax squared plus bx plus c. It's missing this one. To make that term missing, b has to be 0. Well, 1 minus 1 equals 0, and 1 times 1 equals 1. So this is the difference of squares. And if I were to factor it, it would be x plus 1, x minus 1. Okay, that doesn't change its degree, that doesn't change its leading coefficient. We just might have to use that later, okay? All right, so the degree of this one, here is my leading term. This is my degree. Here is my leading term. This is my degree. My 2 degrees are equal. I always want to compare the degrees because that tells me if I need to know what the leading coefficients are. Since they are equal, I do need to know their leading coefficients. So go back and look at P of X. The leading coefficient is 3. And go ahead and look at Q of X. The leading coefficient is the invisible 1. To find my horizontal asymptote, I'm going to go ahead and use that equation where I take my leading coefficient of P and I divide it by my leading coefficient of Q. So that means I have 3 divided by 1. My horizontal asymptote is at y equals 3. My vertical asymptote, I'm going to use my denominator. I'm going to use my denominator, and I have to factor it. So it's a good thing I've done this. I'm going to take my two factors, x plus 1 and x minus 1, and I'm going to set them equal to 0, and I'm going to solve. So I have x plus 1 equals 0, or I have x minus 1 equals 0. This one would give me x equals negative 1. This one would give me x equals positive 1. So I have two vertical asymptotes, one at x equals negative 1 and one at x equals positive 1. Yes, that can happen. All right, let's go ahead and graph them. So let's go ahead and graph. Here is our first vertical asymptote. There we go. X equals negative 1. Here's our second vertical asymptote. There we go, at x equals 1. Our horizontal asymptote was at y equals 3. Now this graph was a little tricky. There we go. Here we go. That's better. This graph didn't really give me a lot of points when I went into Desmos. But what it does is it has a part that swoops right here and a part that swoops right here. And then what's happening in this space right in here, what's happening in this space right in here is there is a piece of the graph. There's a piece of the graph that starts at 0, negative 10 right here, and it's a parabola that goes down like this. But it has to stay right in between negative 1 and positive 1 all the way down. So it's very, very, very tiny. And that's what our graph looks like. So if we were to do the domain, which remember are our x values, okay, our domain would be from negative infinity to negative 1. So it's going to come all the way from here up until it stops right at the asymptote, okay? Then it's going to have this little piece of the graph right in here that's down there. So it's going to go union negative 1 to positive 1. That's that little thin graph, part of the graph in between, that little parabola that's down at the bottom. Union, and then I've got to cover this part of the graph to the rest of infinity. I'm going to put it down here, 1 to positive infinity. Okay, so what's happening is our two vertical asymptotes are splitting it, and I have to talk about the piece leading up to the first asymptote, the part in between the two vertical asymptotes, and then the part after the last asymptote. Whoa, that was a lot. My range, which is my y value, are my y values. It would be, this one's trickier. If I do negative infinity would be down here, and it's going to go until it hits this negative 10. Negative 10 is part of this graph, so it's going to be negative infinity to negative 10, which is part of the graph. Union, and then there's this big gap from negative 10 to negative 3, where there's nothing. There is nothing in this graph right here. Okay, the graph starts here at 3 and goes to positive infinity. Oh, sorry, not negative 3, positive 3 to positive infinity. Ooh, I wouldn't have known that unless I looked at the graph. All right, I have one last example for you, and I've saved the hardest for last. We're going to go ahead and graph the function f of x equals x squared minus 8x plus 12 over x squared minus x minus 6. We're once again going to go ahead and find the asymptotes, the intercepts, the domain, and the range. All right, let's go ahead and take a look at our P of X and our Q of X. Now, when I look at this graph, I can factor it. I can factor this. I know it's going to be, let me grab this color, X times X, and 12, let me think while I grab my color. 12, 2 times 6? Yes, 2 times 6, because 2 plus 6 is 8. So 2x and 6x. And if they're both negative, I would get negative 8 when I add it. So that means my 2 here would be x minus 2 and x minus 6. All right, Q of x is also factorable. Q of x is also factorable. This would be x times x. And let me think, 6. It's got to be 2 times 3. It's got to be 2 times 3 because 2x and 3x, I can make those become negative 1x if this one is negative and this one is positive. So that means, yep, there we go. I've got x plus 2 and I've got x minus 3. Is that correct? I think there was a typo in here. I've done everything correctly, but I think we want it to be this way. I think we want it to be positive, which would mean if it's positive, hold on guys, whoops, nope, I wanted to keep that. What I want to erase is this stuff right here. Hold on. Because if we make it positive, let me get rid of this. They want it positive because they want the x minus 2 to match. They want the x minus 2 to match. And so if we make this a positive x, it actually will work for us. Because notice both of them have, oh, there we go. Both of them have this factor of x minus 2. And for them both to have that, I've got to have a plus x on the bottom. That should be an x squared plus x minus 6. There we go. So my degree, if I go back and look, both of my leading terms are x squared. So my degree on both of them is 2. My degree on both of them is 2, which does mean that they are equal. So I'm going to go ahead and grab my leading coefficients from each one. My leading coefficient here would be 1. My leading coefficient here would be 1. 1 and 1. My horizontal asymptote, hold on a second. Yeah, my horizontal asymptote is going to be that line, my leading coefficient of P divided by my leading coefficient of Q, which is going to be 1 divided by 1. So it's going to be y equals 1. Now I have to be a little bit more careful with my vertical asymptote. If I were to go back and look at my equation, um, let me see. I'm trying to think of how to show this to you guys. Remember we said that you would factor the denominator and you would use these to find your vertical asymptotes. We're going to go ahead and do that. So we have our vertical asymptotes. These are the two that we have, right? So we would have this set equal to 0, which we would add 2 to both sides and we would get 2. And then we would have this one, we would subtract 3 from both sides, so we would get x equals negative 3. But because both my numerator and my denominator have x minus 2 as a factor, a whole is created. Think about it this way. When I go ahead and factor this, I get x minus 2 times x minus 6. When I factor my denominator, I get x minus 2 and x plus 3, right? These two cancel, and this is what I'm actually going to put into Desmos to factor. Because if I put in this, I get a really weird graph, okay? So what's happening, because we share these two factors and they cancel each other out, there becomes a hole there. So this is actually a hole, and my vertical asymptote is it. So it's neither a 0 and it's not an asymptote. My asymptote is only at x equals -3. All right, here we go. So my vertical asymptote is at x equals -3. There's going to be a hole when x is equal to 2. There's going to be a hole when x is equal to 2. So all we did was we went into the equation and we did f of 2 to find it. Now you could do this in Desmos, but really 2 minus 6 over 2 plus 3, which would be -4 over 5. So there's going to be a hole right there. I'm going to do the best I can to make the hole to probably like something like this. There's going to be a little hole in my graph. I tried to draw an open circle, guys. And then, of course, my horizontal asymptote was at 1. Let me draw that in. And let me go ahead and show you what this graph looked like. So I had a point 0, -2, 0, -2, and then -2, -2 +8. No, it must have been -8. Must have been -8. -2, -8. So something like this, but there's a hole right here. Okay, there's a hole right there. And then -4, 10, and -6, +4, something like this. My range. Now, if I were to talk about my range, I'm actually going to go ahead and use it as um, set builder notation, because you guys are not going to have to do domain and range on this graph. So it would be all the x's such that x is not equal to the 2 where the hole is, comma, the -3 where the asymptote is. That's how I would do this one. And my range, which are my y values, all my y's such that y is not equal to my asymptote of 1. And then for my whole right here, remember that's where we did that 2 minus 6 over 2 plus 3, and we got the -4/5.